So what I'm going to do, I will write down the solution, the coefficients of this polynomial in some cases, actually, case n equals 3. So, example, n equals 3. So, what we want is this. Here, we want a polynomial of degree 2, so that at xi is equal to yi for I1 up to 3. Okay, so what we mean is this: we have, let's say, 3 real numbers, and at these 3 real numbers, values of the polynomial are given like this, and I want a quadratic polynomial that passes through this point. Okay, I want to find this coefficient, and using this equation, you can solve it, and what you get is this. Let me write down the solution, and then we will see. I know that there is a unique solution, and I will write down a solution which satisfies this condition. Therefore, it will be the unique solution. And here is the polynomial. And actually, the way I write it will tell you how can you write down this polynomial in the general case, not necessarily in equals to. It is this one. Y1 times x minus x2, x minus x3. So x is the variable, x2 and x3 are just these real numbers, divided by x1 minus x2, x1 minus x3, plus y2 times x minus x1, x minus x3, and then x2 minus x1, x2 minus x3, plus y3. This time you can guess, right? So if you have 1 here, then you don't have 1 here. Therefore, this will be just x minus x1, x minus x2, and here you will have just x3 minus x1, x3 minus x2. So I claim that this is the solution. I don't need to solve this, matrix equation to verify that that's the solution. It is enough just to check that this polynomial satisfies these conditions, right? Because we know that there is a unique polynomial which does this. So if this polynomial satisfies this equation, then this should be the solution. Let's check. For example, let's see P of x1 is equal to y1. Let's see if this is the case. Well, when you plug x equals x1, let's see what we get. When I plug here x1, so I will have x1, x1, right? x1, x1, x1, x1. You see, I have the x1 minus x1, therefore this thing is 0. So all these terms are gone. When I plug x1 here, this is 0. Therefore, this term is gone. Only I have this term surviving, right? And what is this coefficient? X1 minus x2 divided by x1 minus x2, x1 minus x3 divided by x1 minus x3. So all this coefficient is just equal to 1. Therefore, P of x1 is just y1 times 1 plus 0. So P of x1 is just 1. Sorry, y1. Tamam mı? Similarly, so this implies P of x1 is just y1. Therefore, I mean, if you just repeat it, x2 will be y2, and P of x3 is just y2. And from this solution, you can write down the solution in the general case, right? Yazarsın değil mi? Genelde nasıl olacak? Yani bunu n eşittir 3 yerine n olsaydı ne olur? Değil mi? Onu size bırakayım. Yani denklemi çözmenize gerek yok. Çözümün hani tahmin ediyorsunuz ve o sağlıyorsa o zaman tek çözüm o zaten. Tamam mı? Anlaşılmayan bir şey varsa hani hemen durdurup sorun. Peki.
O kısmı nasıl ifade ediyorsunuz? Yani bu şekilde yapacağınız.
Olur mu? Yani bu klasik bir şey biliniyor. O yüzden direkt çözümü yazdım yani. Şey değil, hani bunu bulmanın bir nasıl diyeyim işte böyle mantıklı bir şey yok falan yok. Ama şunu biliyorum, tek çözüm olduğu için, tek çözüm olduğunu biliyorum. Dolayısıyla bir tane çözüm yazarsanız o tek çözüm. Başka oyunlar.
Hocam bu konu numerik yaklaşım. Uzak bir oluşum.
Yok bu şey yani exact solution. Yani yaklaşık bir çözüm değil. En tane nokta verildiği zaman düzlemde tabii x aylardaki olmak üzere o en tane noktadan geçen derecesi en fazla n-1 olan tek bir polinom var. O polinomun ne olduğunu söylüyor. Yani approximation. Nümerik analizde ne kadar kullanılıyor bu bilmiyorum. Hani kullanılıyordur ama bu hani her amaç için uygun bir polinom bulma yöntemi olmayabilir. Onu hani, nümerik analiz çalışan insanlar. 381 ders alırsanız orada dünya kadar başka algoritma görürsünüz. Okay.
Hocam, benim kafamı karıştıran şey şu. Yevan'ın mesela yanına yazdığımız koefficient'ı nasıl belirliyoruz? Bizim o bildiğimiz kurallar vasıtasıyla değil mi? İşte bunlar birbirine bölünmüyor gibi bir şey.
Bölünmüyor derken?
Yani x minus x2, x1 eksi x2 görüşemez gibi bir şey.
Yok bir şey düşünmedim. Yani direkt kağıtlarını yazdım. Dedim ki tek bir çözüm olduğu için çözümü nasıl bulduğunuzun önemi yok.
Hepsi hiç geçerli.
Bulduğun sürece geçerli.
Ne yapayım?
Yani o işin eğlenceli kısmı. Onu bilmiyoruz. Yani bir sürü sorunun cevabını bilmiyoruz. Bu yani klasik bilinen bir şey. Ama bir yandan da şunu söylüyor işte hani tek bir çözüm olduğunu biliyoruz. Tamam mı? We know that there is a unique solution. Right? The linear algebra tells us that there is a unique solution. And what is the solution? Well, it is computed probably several hundred years ago, and it is this one. Tamam mı? Okay. Now I'll talk about canonical forms, characteristic polynomial, and so on. I will not follow the book for the canonical forms. I have my own notes. It is, I guess, similar to what Cemal Koç wrote in his notebook. But it is not exactly the same. While we are studying canonical forms, along the way we will also study so-called symmetry normal form. And actually that is also related to other things in algebra. But that, symmetry normal form is a very powerful tool to study the characteristic canonical forms. Canonical forms basically diagonalization and Jordan form. If you remember from last semester, there are some matrices which are not diagonalizable. Like, for example, a matrix like this, let's say 2, 2, 1. Okay, this matrix is not diagonalizable. And actually, this is the best form you can get. It's called Jordan canonical form. And we will see how we decide whether a matrix or linear operator is diagonalizable or not. And if it is not diagonalizable, how can we find its Jordan form? And so on. So we will study those problems. And a tool to study all these is so-called symmetry normal form. Again, last semester, actually, I talked about it while we were discussing systems of equations, but I'll just go over all of them and tell you what is symmetry normal form and so on. It's the kind of magic. I mean, so that symmetry normal form is something very nice. It gives a lot of nice results. So let's see. And along the way, I need to define some algebraic concepts like modules. So it's like a vector space, but instead of field, we will have a ring, like integers. Like integers is a nice ring, but it's not a field because 2 has no multiplicative inverse. But in that case, we obtain so-called modules, and their theory is a little bit similar to vector spaces, but they are much more actually complicated objects compared to vector fields, vector spaces. Kamera çevirelim. Peki. So let me. Okay, so canonical form. We will study diagonalization of operators and Jordan canonical forms of operators. The main tools we will use is so-called symmetric normal form. Or the matrix forwards in PID. Principal ideal body. This is something actually you will see in abstract algebra, but I'll just show you two examples of PIDs. Actually, you know all these. One of them is integers. The other one is the polynomial ring over a field, like Rx, one variable polynomials. They are PIDs. And we will use those gadgets to study canonical forms of operator. Okay, now first of all, ringi aslında gördünüz değil mi? 116'da.
Evet.
Ringi gördünüz. Şey gördünüz mü? Ideal nedir falan. Gördünüz. PID gördünüz mü? Gördünüz. So, let me start with the ring. So, the ring R plus and product is a triple that R plus is an abelian group. And this is also from R plus R into R is a binary operation. So this product and multiplication are compatible with each other. So A times, for example, B plus C is just A times B plus A times C. And actually, I will ask the multiplication to be commutative in the following sense. So A times B is equal to B times A, commutatively. Not all rings are commutative. For example, matrices under multiplication is not a commutative operation, right? A times B is not equal to B times A. So matrices form a ring. But in our case, we will only consider commutative rings. Of course, the product operation is associated in the following sense. A times B times C is just A times B minus 2. It's associated. And so what are the examples of such objects? Of course, you know, integer is usual addition.
Hocam, what about the inverse? What about the inverse of rings? I mean, for example.
We don't require that elements have multiplicative inverse. That's not something we assume in case of rings.
Okay, hocam.
If every element has a inverse, multiplicative inverse, then it's called division ring because you can divide, right, elements. And if it is commutative, then it is called a field, actually. But a commutative ring, in a commutative ring, you don't require elements have multiplicative inverse. Of course, you know, this is a field, but it is also a ring. Here, every non-zero element is an inverse. Of course, we can also consider this ring or complex number, any field actually, any field. And what else? Our basic examples will be this one, and the other one will be a field X in it, and then addition and multiplication. So polynomial ring, okay? Polynomial ring, Kx, the set of all polynomials. So these are actually our basic examples that we will consider while we are studying canonical forms. What's a principal ideal domain and what's an ideal? So let R plus prime and product be a commutative ring. A subset I of R R is called an ideal of R if it satisfies the following conditions. I, with respect to the addition operation, should be a subgroup, right? I know that R with plus is an abelian group, so I with that operation, addition operation should be a subgroup. If so, I with this operation is a subgroup. In other words, it is closed under addition. If you have two elements, their sum is there. And second, and of course, it should have, every element should have its additive inverse, right? Because it's a subgroup. And the second condition is the following. For any R in R, R times R. So what I mean is this. You multiply elements of R with R. So you look at things like this. Okay. So this should be a subset of this. In other words, it is closed under multiplication with an arbitrary element of the ring. So if you have something in the ideal, and if you multiply that element with an arbitrary element of the ring, you again obtain an element in the ideal. Okay? If this is the case, then we just say that I is an ideal. In case R is not a commutative ring like matrices, these definitions are more complicated, because then you have left ideal, you have right ideal, and so on, because multiplication from left and right are different things, and so on. So things get complicated. But for us, commutative rings are good enough. So our life is easy in that sense. Okay. Example. So, for example, consider integers. So, an ideal here is what? For example, all even integers is an ideal, right? 2 times n is an integer is an ideal, right? Neden? Because even integers is a subgroup, right? Sum of 2 integers, even integers is even. Difference is also even. And if you multiply an even integer with any integer, you again obtain an even integer. So it satisfies both rules. And actually, in this case, you see, all the elements here are multiples of 2. That's why we usually write it this way. So this ideal is generated by 2, meaning that every element here is just a multiple of 2. Okay, so this means so this is exactly this gadget. So short notation, 2 times n is in Z. Such an ideal is called a principal ideal because it is generated by a single element. Okay, so let me write it here. If is a commutative ring, for any let's say R, not R, S only, R, the set. Bunun ne olduğunu yazıyorum. S'in generated ideal. The ideal generated by S means the following. R times S where R is S. R in R. Yani S'in tüm katlarına bakıyorum. Is an ideal. Of R. Right? This is an ideal of R. Why is that? Because if you choose 2 elements in the set, their sum is also in the set. Let's check that. Okay. So let's say this is R. If you take so this gadget with this operation is a subgroup. Why is that? Well, take 2 elements, RS1, no, RS, R1S, R2S, right? 2 elements in this set. S is fixed, R is an arbitrary element of R. Let's take 2 elements like this. Then their sum is what? This is just R1, R2 times S. Therefore, it is just another element times S, so this is also in I. And also, if R times S is here, then of course minus R times S is also here, because this thing is just minus R times S, right? It is again a multiple of S. Değil mi yani? R çarpı S bunun içindeyse onun eksilisi de burada. Çünkü eksilisini bulmak için eksi R ile çarpacaksınız. O kadar. Diğer koşul ne? So this shows that this is an abelian, subgroup. What about the other condition? Other condition is that multiple of any element here also lies in the R group. Well, that's also true. If let's say R is in R and X is in I, then X is in I means it is actually some ring element times S. Then this X is just, let's say, R prime times S, right? For some R prime, thus R times X is just R times R prime times S, but that is R times R prime times S. So what we get is some other element of the ring times S, but that's clearly is in I, right? Therefore, I is an I group. Okay. Nasıl?
Şimdi ayrı olduğunu kalkmak istiyoruz.
Hı hı.
O özelliklerini kalkmak gerekiyor. Ama sonra ayrı sarf hareket, işte ayrı hareket ve S'in de ayrı dahil olacağını ayrı olması nedeniyle.
Ama tanımı öyle zaten. Onu kullanıyorum. Yani bu şunun ideal olduğunu söylüyorum. Bu tanımı gereği
Ayrı olarak, ne olarak ayrı
burada şey örneği veriyorum. Hani bu ay dediğim şey bir ideal. Örnek, ideal örnek. Herhangi bir eleman alın. Onun bütün katlarına bakın. O rengin içinde bir ideal görür. Tamam mı?
Hocam aldığımız elemanla çarptığımız şey ikisi de komutatif ringin içinde mi olmak zorunda?
Ya tabii her şey komutatif ringin içinde. İdeal de onun subseti zaten.
Peki hocam.
Anlaşıldı mı? Şey gibi geliyor herhalde. Zaten ispat etmek istediğimiz şeyi kabul ediyoruz gibi. Evet. Hoca bizi kandırıyor. Evet.
Hoca bizi yiyor.
Kandırdığım yerler olacak da onları pek hissetmeyeceksiniz. Okay.
İdeal yapan şey ne?
Efendim?
Saklı, ideal yapan şey ne? Farklı.
Farkı şu. It is closed under multiplication by arbitrary ring elements. So, if you have an element in the ideal, if you multiply that element with any element of the ring, you still get an element in the ideal. Okay, that's the important actually distinction between a subgroup and an ideal.
Hocam bir tane örnek verebilme şansınız var mı? Şu ürün sürmeyeceksiniz. Ideal. Yani her ideal örneği verebilir miyiz?
Yani mesela şu işte hani Herhangi bir eleman al. Herhangi bir eleman al. Efendim? Mesela reel sayılarda iyi soru. Reel sayılarda pek ideal yok.
Ben de düşündüm işte.
Reel sayılarda yok. Integer'larda var da reel sayılarda yok. Şimdi integer'larda right actually okay, let me just işte bir kendisi var bir de sıfır var. Oyun başka yok. So if k plus is a field like real numbers, then it has only two ideals, which is just zero ideal. It has only zero element in it, and k itself. Okay. Ring, commutative ring, but every element has multiplicative inverse. Non-zero element has multiplicative inverse. Efendim?
Bu ideal olabilmesi için sadece kapalı olması yeterli mi yoksa abelian olması da gerekli?
Ya şey tabii o bu şeyin içine saklı olacak. Ringin içinde saklı.
Oyun ve abelian.
Efendim?
Ring olması için abelian olması gerekli mi?
Yok gerek. Ben sadece burada bizim işimizi görecek şeyleri kaldı. Yoksa hani genel bir teoriden bahsediyorum. O zaman tanımlar falan karmaşık hale geliyor. Onlarla ilgileneceğiz. Bizim için ring komik. Tamam mı? Şimdi şunu görelim isterseniz niye bu doğru? Let R diğer ideal so that it is not zero ideal. Like zero consisting of just zero element. This set is an ideal. Like that, it is closed under, I mean, it's a subgroup, right? Consisting of just the identity element. And it is closed under multiplication because R times zero is okay, so it is closed under arbitrary multiplications by elements of the group. Suppose that this is an ideal, but it's not the zero ideal. Then I claim that this is the whole thing. Why is that? Since this is not the zero element, it has a non-zero element. R, the element here, so that R is not zero. Değil mi? Madem bu sıfır değil, bu ideal, o zaman sıfırdan farklı bir eleman. Ama bu field, this case of field, every non-zero element has multiplicative inverse. So, since case of field, R has a multiplicative inverse. Say R to the power minus 1. Yani ne biliyoruz? R times R to the power minus 1 or this is just 1. Okay? Ama bu ne demek? Well, first of all, I wrote one as r to the power minus 1 times r, right? So r to the power minus 1 is an element from the field. R is from the ideal, right? This is from the field. This is from the ideal. But we know that if you multiply an element of an ideal with arbitrary element, you get something in the ideal. And in this case, we get 1. Therefore, this will be the ideal. So our ideal contains 1. But then, if, let's say, x is any element of the ring, then x, which is equal to x times 1. But again, this is from the ring. This is in the ideal. Therefore, the product is in the ideal. So what you get, if you have any element in the ring, then it is in the ideal. This implies that the whole ring is in the ideal. But we know that by definition, this is a subset of R. Therefore, we see that our argument is the whole ring. In this case of the yani R dediğimiz durumda K. Tamam mı? Dolayısıyla bir field'in içinde iki tane ideal. 0 ve ring'in tamam. Başka ideal. Ama integer'larda demir bir sürü var. Her sayının katları. Yani şu ring'i alırsak for any and z, this is an idea. Nedir bu? N'nin katları, yani k times n'ler is an idea. Bu durumda da ne biliyoruz aslında? Bunlar ideal ve başka idealler, tüm idealler. So, claim any ideal I of Z is of the form her ideal bir şekilde olmalı. Bir sayının katı, başka ideal yok. O yüzden Z diyeceğiz. Z that's the reason why we call Z a principal ideal domain. Meaning that every ideal is principal. So as this, it is generated by a single element, every ideal. Okay? And why is that? Bunu da görmüşsünüzdür 116'da. Gördünüz mü? Division algoritmi. Integer'lerde bölme var.
Hocam tahta.
Tamam, çevireceğim. Okay.
Bir de biraz geçiyorum. Hemen.
Olabilir. O yüzden silerken çevirmiyorum aslında. Ama dediğin doğru. Yani muhtemelen öyle oldu. Peki. Okay, let me just do this. Okay, let me add an idea. Let's say now this ideal has, if it is not the zero ideal, assume that this is not the zero ideal. Okay, so it has non-zero elements. If it is a negative element, then -1 times that element is a positive element. Therefore, a non-zero ideal has always positive elements. Okay, and what I will do, I'll consider the smallest positive element in that ideal. So let's S be the minimum of what? The set of all elements in I such that X is positive. Yani bu ideal içindeki pozitif tam sayılara bakıyorum. Onun en küçüğünü seçiyorum. Bunu seçebilirim. Neden? Çünkü integer'larda hani eğer alttan sınırlıysa, yani eksi sonsuza kadar gitmiyorsa kümeniz, o zaman her kümenin minimum elemanı var. Değil mi? Integer'larda var. Reel sayılarda, rasyonel sayılarda yok. Değil mi? 1 bölü n dizisinin ya da kümesinin en küçük elemanı yok. Çünkü 1 bölü 100'den daha küçüğü var, 1 bölü 200. Ondan da küçüğü var, 1 bölü 400. Değil mi? En küçüğü yok ama integer'larda var. Bir yerden sonra direkt sıfıra iniyor. So let's S be the minimum element of the set of positive elements in the ideal. Of course, this is an element that S is an element here. I claim that S divides, so subclaim, S divides every element in I. Yani S integer'ı S'nin içindeki her şeyi böler. Dolayısıyla every X is a multiple of S. Neden? Proof suppose not. Suppose S doesn't divide some X or some X. But then division algorithm tells us what? If this integer doesn't divide this integer, then I can write the following. X is just like this. 2 times S plus some R, where R is between 0 and S. Değil mi? Yani bölme algoritmasından onu elde ederiz. Bir kalan olacak. Kalan da böldüğünüz sayıdan daha küçük ve pozitif bir şey. Ama şu var şimdi elimizde. This is in I. Right? S is in I. S is in I. Therefore, 2 times S is in I. So this is in I, this is in I. But then I can write R to be X minus 2S. This is in I, this is in I. I is an abelian subgroup, it's a subgroup, therefore this is still in I. So what we get is that I obtain an element in I, it is less than S and still positive. But that's a contradiction because S was the smallest element in this set among the positive elements. But here I found something less than that, right? Yani bu en küçüktü ama daha küçüğü buldum. Değil mi? Bu contradiction. İşte contradiction. Try to obtain a contradiction because I assume that there is some x so that s doesn't divide that element. So this is false. It means that every element here is divisible by s. In other words, every element is a multiple of s. Therefore, our ideal, right? So this is a multiple of this. In other words, this is generated by s. Okay. So that's the proof. Burada bitirelim. Bir dahaki derste polinomial algebradan bahsedeceğim.